thank you for your nice introduction, and it's really a great pleasure for me to be here today and talk to you about our work on lignin nanoparticles. So I will tell you today about their surface properties and give some examples of their use in specifically in adhesives, coatings, and also for energy storage. So the outline of my talk today will be, first I will give you some motivation why we go through this method of making the spherical lignin particles and why we don't use the crude lignin as such. And then I will tell you a bit how solvent and lignin source affects the particle properties. And one important thing that we have found is that making these particles actually affect the surface chemistry. So the surface chemistry is different from the surface chemistry of crude lignin. And this will, of course, have an effect on the performance in the application also. And then I will give you some examples of the applications, for example, for coatings and adhesives and hydrogels. For I will not talk about emulsions today. So I don't think I need to motivate why to use lignin. I assume everyone following this seminar series knows that lignin is a really cool material. It has a lot of inherent nice properties. It can act as a radical scavenger, so it can protect against oxygen. It can protect against UV degradation and against microbes. It is in the wood, it also is acting as an adhesive. So there's a lot of research on lignin-based adhesives also. So lignin is great, but it is also, everyone that has worked with lignin knows that it's not an easy polymer to work with. It's heterogeneous. Depending on the source and the extraction method, you get a different molecular weight, you get different chemistry, different bonds. So it's not very reproducible and it's quite complex, and there's a lot of arguing about the exact structure of lignin, because when you extract it, it of course is modified, so it's difficult to say what the structure in the native wood is. So we want to have a more reproducible and tunable material to work with. And for this, making this colloidal lignin particles, spherical particles, is quite useful. And this is also a very simple and scalable process. So one can prepare lignin nanoparticles in different ways. In my group, we are using this nanoprecipitation method, and it's quite simple. So we take the lignin and we dissolve it in an aqueous organic solvent, for example, aqueous acetone or aqueous THF. And then you take this dissolved lignin and pour it into water. And since the lignin is not soluble in water, the water acts as an anti-solvent. The lignin spontaneously self-assemble into spherical particles. And these particles have a negative charge and they stay very stable. So you get a stable aqueous dispersion of spherical lignin nanoparticles with rather well-defined size, around 100 nanometers. But does the lignin source affect the CLP properties anyway? And especially important is, can we tune the properties? So for this, let's first look into the effect of lignin source on the particle properties. So one thing that we have found, and also many others have found, is that the higher the molecular weight of lignin, the smaller the particles. If you, this first picture here, here we have used different solvents to fractionate the lignin. And if you look at the numbers here, those are telling the molecular weight in the, of that material. So not to go into details here, but if you, for example, look at this one here, the soda lignin, it has a molecular weight around 2000. Then if you fractionate with aqueous acetone, we have a higher molecular weight here of 7000. And if we compare these, we see that their size almost decreases to half. So this is quite clear that the molecular weight is affecting the size, so that the higher the molecular weight, the smaller the particle size. The same thing was found in another research study where we used enzymes to polymerize the lignin before forming the particles. So here also having the higher molecular weight leads to smaller particles. And this is most probably due to the solubility, also solubility in water especially, decreases with the higher molecular weight. So the nucleation is probably faster, and then we get smaller particles. But it's not, I think I would say molecular weight definitely affects. That's a clear effect, but it's not the only thing that affects. So if we have compared the kraft lignin, soda lignin, and soluble hydrolysis lignin as the source for the lignin to make the particles. And then we have used either aqueous THF or aqueous acetone. And if we, for example, compare the soda lignin and the hydrolysis lignin, we again see a slight decrease in the particle size. And this is partly due to the higher molecular weight here, but it's also most probably due to a difference in chemistry. So the hydrolysis lignin is more condensed, again, probably having more hydrophobic parts. So it's also, again, nucleation is faster, and we end up with slightly smaller molecular weight. But of course, in reality, you can't always choose the molecular weight or choose the lignin you have. You probably have one lignin that you need to use. So is there any way we can tune the size irrespective of what lignin we are working with? And yes, there is one easy way. So that I will show you next. And then I will continue to talk a bit about the surface chemistry of these lignin nanoparticles. So the size of the particles can be easily tuned by choosing the solvent system. So this we can see, for example, if we compare that we use aqueous acetone for the dissolution or aqueous THF. If we use the aqueous acetone for the dissolution of lignin, and then we form the particles, we end up with quite a narrow size distribution with a size of 90 nanometers. This is determined using dynamic light scattering. So if we would determine the size from the TEM images or AFM images, it would probably be a bit smaller still. But here you can see AFM images of these particles prepared using aqueous acetone. And here are the particles using aqueous THF for the dissolution of lignin. And there we get an average size of 140 nanometers, so clearly larger. So this is a very simple way of tuning the size a bit by choosing the solvent. And this we have looked into, but what the reason for this is, and it is about, it can be explained by the interactions both between the solvents, so between acetone and water, and also between the solvents and the lignin molecules, and that those leads to the formation of faster nucleation and from the acetone system and smaller particles. But unfortunately, this is still unpublished results, so I'm not showing those today. About surface chemistry, I think this is something that is worthwhile considering. So when we are forming the lignin particles, they self-assemble so that probably the core is formed by more larger molecules and more hydrophobic molecules. And then the smaller molecules with more carboxylic groups and more OH groups and the more hydrophilic molecules are then assembled on the corona. So that makes the particles actually quite hydrophilic. And if we compare to normal lignin, the CLPs are more hydrophilic. And this is, of course, one reason why we can have the stable aqueous dispersion also. If it would be hydrophobic, it would, of course, phase separate from the water. But what you can see here is that the water contact angle measured on model surfaces coated with the colloidal lignin particles, either made from THF or acetone, or then a model film made from dissolved lignin. And you can see that we got the typical about 60 degrees contact angle for the lignin. This is quite typical, also reported in literature many times. And it's not affected by the relative humidity during measurements. But for the colloidal lignin particles, we get a much smaller water contact angle, so they are more hydrophilic. And interestingly enough, if we increase the relative humidity, some water is probably bound to the surface, making them even more hydrophilic. So this, you can make two conclusions from this. First of all, I would say that it's very important, if we want to understand the interactions, that we actually use these kind of model films that are made from the CLPs, because they better describe the system than if we would be using this dissolved lignin. And the other thing is that it shows that actually we have a different surface chemistry, so we might have a bit different properties in that, or they might work a bit different in applications also. And this is good to keep in mind. Especially, I think these particles will be quite nice in hydrophilic media, either in a composite together with hydrophilic cellulose or in aqueous media. This is further some example of polymer adsorption. Compared again the traditional lignin model film, which describes other type of lignin, more hydrophobic lignin, and then the CLP coated particles, so the adsorption to these colloidal lignin particles. And this is a QCMD measurement. So if we have a decrease in frequency, that means that we have adsorption at increase in mass. So the larger the decrease, the higher the adsorbed mass is. And we can see here a clear difference that more of this soluble cationic lignin is adsorbed to the CLPs compared to lignin, but it adsorbs to both surfaces. So indeed, this cationic lignin is interacting with the surfaces, both via the pi-pi interactions, or interactions between the phenol groups, and also by electrostatic interactions between the cationic groups on the cat and the anionic hydroxyl groups, that we have maybe more accessible carboxylic groups in the CLPs compared to the dissolved lignin, but of course we have them in both. And another thing that is different between these two model films is, of course, that with a CLP film is made from small spheres. So we do have a higher roughness and higher accessible surface area, and that will also increase the adsorbed mass. pH stability is also quite important when we are using this. So we already knew from previous work that at pH is like above 12, these particles dissolve, because lignin, this craft lignin that we have used in these experiments, dissolve at high pHs. But using these model surfaces, we were able to get a bit more detail into how the changes in pH are affecting. So if we start from pH 6, we see that almost no change at pH 8. So there's very little swelling of these particles. This is quite different from nanocellulose, for example, which swells a lot with changes in pH. So these particles are quite rigid. And the only thing we are seeing is that we have some adsorption of water molecules at the surface of the particles, which increases the weight and increases the change in dissipation at pH 8, and then at pH 10 a bit more. But at pH 12, we see an increase in frequency, meaning that we have a decrease in mass. So this shows clearly that they are totally dissolved at this pH. But we notice with these more detailed measurements that the pH 10 is kind of the soft spot, very sensitive spot. Sometimes we see clearly dissolution here. Sometimes we see only swelling. But also when we looked with AFM afterwards, we saw that the particles had become a bit smaller. So we start to have dissolution of the most soluble small molecules from the surface. And this is, of course, something that was only possible to see with these methods and not in the bulk measurements. So that was a bit about the surface properties. So now that we know how these particles, what kind of surface they have, how they behave, now we can go through a few examples of their applications. So I will focus on coatings and adhesives and energy storage. One interesting thing with this, with the method of making these particles, is that we can prepare hybrid particles. And using these hybrid particles, we can produce water-resistant adhesives for wood, for example. We can make solvent-resistant particles, and that can also withstand higher pHs. And we can make phase-changing materials for energy storage. And making of these hybrid particles is as simple as making the particles themselves. So if we have another component, another molecule that can be dissolved in the same aqueous acetone, for example, and does not dissolve in water, we can form these hybrid particles. And this we have done with a few different systems for different applications. And we still have the negative charge on the surface due to the lignin molecules at the surface. So the first example I will show you is the combination of bisphenol A diglycidyl ether, called BADGed, and lignin and the lignin. And this BADGE then enables making either inter or intraparticle cross-linking. So when we mix the two, we get the hybrid, we can form these hybrid particles. And if just by tuning the ratio between the crosslinker and lignin, we can get to two different things. We can either get intraparticle crosslinking. So we are stabilizing the particles so that it withstands solvents that would otherwise dissolve the lignin, and it also withstands high pHs. And these crosslink particles can be used for example, covalent surface functionalization, but also if we want to use them in more harsh conditions. And if we have a higher amount of the batch again, then some of it is released to the surface, and we can make dry and wet adhesives. So if I first show this stability, again using QCMD measurements, but here we have already calculated the change in mass. So when we adsorb particles, we get some change in increase in mass. And then if we have unmodified particles, which are this, which is the green line here, when we get to 11 or 12, then the particles dissolve and the mass goes to 0. But if we have cured particles, we see that they are stable even at pH 12. Interestingly enough, when we had the hybrid particles, but they were uncured, they were still rather stable. So even if we are not heating them, we still see this, that they have cross-linked, so they have become more stable. And looking at AFM images, we can see that if we have unmodified lignin particles, they are totally removed, either with acetone rinsing or rinsing at high pHs. But if we have cured particles, they are, you can see them also after rinsing, either with a solvent or at high pH. And they work well as adhesives also. If we, for example, look at this here, we have the dry adhesive strength is somewhere around between 5 and 6 megapascal, which is quite comparable to commercial epoxy, a bit lower. But what is interesting is that we get excellent wet strength. And if you have worked with lignin for adhesives, usually you have lousy wet strength. So that you have, but these have quite high wet strength also. Okay, another example of using hybrid particles is to make these water dispersible capsules for phase change materials. So here we wanted to use also natural phase change materials. So we used different fatty acids, for example, lauric acid or tallol oil fatty acid. And again, same principle, we dissolve both components in the solvent, and then we precipitate in water, and we form these hybrid particles. And these can then be used to store energy during heating, and then discharging heat when it's cooler. So you know that the phase changing materials, the way they work is that when you add heat, then they melt, and then they release heat upon solidifying again, and this can be utilized. But of course, if you would have only the lauric acid, when it's melting, it's difficult to keep it somewhere. You have to have it in a container somehow, have it encapsulated. So that's why lignin is also good to encapsulate this. But there's other advantages of the lignin also. If we here look at the pure PCM, so here the pure lauric acid. We can see, compare the first solidification with the last solidification. We see a difference here in the curve. So we see that this is unstable. You have unstable melting and solidification. And this is, of course, not good if you are using this as PCM materials. When we use the hybrid nanocapsules, we can do this heating and cooling cycle for almost 300 cycles, and it's exactly the same, so it's much more stable. So this works, could work so that it's when it's warm, it's charged, they melt, the lauric acid inside, the PCM inside melts, and you have no need to cool the home with electricity. And then in the night, when it's again colder, heat is released when it solidifies, and so this can be used like that. What is interesting with these nanocapsules compared to other phase-changing materials is, of course, the possibility actually to utilize it, that you could pump this, because they are water dispersible nanocapsules. So this could be interesting from this point of view. Okay, we have also used these lignin nanoparticles to make coatings that we found were both durable and multi-resistant. So they were resistant for UV. They could protect against UV degradation and protect against water, and also solvents did not affect this coating. This is also still unpublished results, so I'm showing just more this teaser here that we can also prepare this in quite large amounts. So this is this stool here has been coated with this nanoparticulate coating. And just how it works, that the good thing with unmodified wood is that it's moisture buffering. So it can, when there's a lot of people in a room, it can, and it's becomes a lot more moist in the air, it can absorb the moist, and then when it's drier, it can release the moist again. But of course, the disadvantage is that it also absorbs water, liquid water, and this we want to avoid. So with traditional coating, we are avoiding both things. So yes, we can protect against water, but usually after painting or using lacquer, this wood is not moisture buffering anymore. But with a particulate coating, we can get both of these effects. And we have also used these CLPs for 3D bioprinting material together with cellulose nanofibrils. And I will not talk so much about these results, but what we saw was that these solid particles inside the hydrogel increases the viscosity at 0 shear rate. That you can see if you are zooming in here. At 0 shear rate, you can see that the higher the lignin nanoparticle concentration, the higher the viscosity is. And interestingly enough, we also saw that there was no cell toxicity observed due to the lignin particles. And this could be used then to get higher printing resolution and also a bit more stable printed scaffolds. And of course, we can, the fact that we can incorporate the lignin particles and they show no cell toxicity, then we can also utilize their antioxidant properties and antimicrobial properties, which might be quite useful in many of the biomedical applications. But as a last thing to talk about, I think it's important when we do a lot of interesting experiments in the laboratory to to think also about what is needed if we want to go from the laboratory to the market. What will the customers ask first? They will ask about scalability, safety, and sustainability. And we're going to need data on all these things to be able to go from the laboratory to actual applications. About the scalability, just for making the particles, the continuous flow is possible and the cost is quite reasonable. We are also calculating now on the scalability of making the coatings, for example, and those look quite promising also. And then about the safety, if we look at the cell viability test, I already said that if we, in this cellulose nanofibrils colored and lignin hydrogel, that there was no cell toxicity found. So here the cell viability was measured using the optical density, and we see that there is growth of cells, more and more cells are growing. And if we look at the medium amount of lignin particles, like 5 or 10%, we see no negative effect at all. With a higher amount of lignin, we see a bit of a negative effect. It's not cell death, they are still growing there, but they are growing less. But we think that this is due to the fact that the viscosity is increasing, so the nutrients are not flowing as easily within this hydrogel. And when we looked at how the cells grow in the scaffold, we can see that they grow also inside this scaffold with the highest lignin particle concentration, which in our mind shows that these are not toxic to these cells that we studied. And ecotoxicity is also quite important, because actually lignin is biodegradable, but not very fast degradable, and it's not according to there's still something left. So it's good to also look at the ecotoxicity, which I will do next. We have done some work on the LCA, and you can read in this article a bit, and some people are working on it, but this is something that needs much more attention in the future. And especially important is to kind of not study only the production of the particles, but actually the use of the particle in an application, and then try to assess whether this is more sustainable than the material we are trying to replace with the CLPs. And there's a lot to be done in this respect, I think. So very quickly about the ecotoxicity. So we studied, or actually our collaborators in this paper studied the toxicity against Daphnia magna, this guy here, and an algae, and studied how at what concentration caused like 50% reduction in living population within 48 hours for this guy, and then against the algae, we again had a similar way. So to study this ecotoxicity. So here are the results, and we studied soda lignin CLPs, either anionic, unmodified, or cationized, and then the soluble hydrolysis lignin CLPs and cationic CLPs made from the hydrolyzed lignin. And if we look at the Daphnia magna, we see no inhibitory effect at all. So for any of this, interestingly, also the cationic is not bad either. And for the algae, we see some inhibitory effect, but still much lower toxicity than for inorganic particles that could be used for similar applications, for example. So this is still quite positive results, and so we think that this is good. So to conclude, I would say that these spherical colloidal lignin particles have a potential in many applications. I showed you, I hope I have convinced you about this also with the application examples I showed you. But it's very important to understand their surface properties to be able to use them in the best possible way. And there are scalable processes to produce the particles, and they seem to be quite non-toxic. So with this, I thank you for your attention, and I'm open for questions.